Now let us turn to the page 1.16. In the page 1.14 and 16, actually those materials used to describe the behavior of frame speed influenced by the Lewis number. We already introduced it in last video, and up to now, actually, we try to give it some understanding about the nature of propagating frame speeds. From the first part, we're dealing with the flow structure of a so-called one-dimensional flow. That means that the propagating premixed frame stabilizes at certain points. Based on this mechanism, you realize how to determine the position of your premixed frame. Basically, it is the balance between the supply velocity and the frame speed. Okay, and I emphasize there is two important burning characteristics, which meaning the frame temperature and the frame speed can be used to identify the burning strength of a given premixed frame. And I use the Bunsen burner frame and also the premixed frame in stagnation point flow or opposite jet flow, try to have a more understanding about the flow structure of a burning premixed frame. Those frames we described earlier, basically dealing with the frame speed and also the frame temperature, actually they are steady burning. Now we are thinking about the transient state for premixed frame, which means we're dealing with the initial state of premixed frame. That means how can we ignite a premixed frame? And later on, we will think about the other transient state. That means the extinction, how the premixed frame can be extinction. The extinguished premixed frame is one of the transient states we need to identify. Here, now we change our focus point from the steady state of premixed frame to the transient state for premixed frame, including the ignition and the extinction. The behavior of ignition and extinction can be described basically from this figure shown in your slides in page 1.16. Okay, let's look at these figures. The horizontal axis actually is denoted by the so-called Danko number, and the vertical axis actually you can use the burning rate to emphasize the variation of the burning strength. Okay, I think it is easier to understand the burning rate if you go to the higher position of along this vertical axis, then you will have a higher burning intensity in representing the higher burning rate. Okay. Now we try to give you some understanding about the definition of so-called Danko number. Basically, Danko number dA is defined as the ratio between the catalytic flow time and the catalytic reaction time. We bring these two times together because we are thinking about how can you ignite the premixtures in a certain control volume. You will think about in your imagination, you try to think about there is the control volume, it's virtual control volume, and inside of control volume consists of a premixture of fuel and oxygen. Okay. Now, in this sense, the fuel is well mixed with oxygen, right? They are ready to be ignited. Then you supply energy into this control volume, then the chemical reaction starts. But you remember when you have a given control volume, you may sense that this control volume maybe exists in a flowing medium, right? The flow is continual movement, and you realize in this control volume there is an influence coming from the flow convection, also the diffusion. Inside of your control volume, there is a certain amount of fuel and oxygen. The concentration may different with the concentration outside the surrounding. Now you will have a diffusion process, which means you think about those molecules of fuel and oxygen ready to react, but they still have some influence coming from the flow, and the oxygen or fuel radicals can be brought out from the control volume to the surrounding, right? That means that we try to complete a chemical reaction inside of control volume, then they can release heat, and this heat can be used to perceive further reactions, because this is the mechanism for premixed flame. They will initially absorb a certain heat from maybe the spark, okay, the heat supply from the outer surrounding. Then they initiate the chemical reaction. Then this chemical reaction will release the heat of combustion. Those heat combustion will be used continuously to pursue next chemical reaction one by one, one by one. Then the flame can have this propagation characteristics. Now you are thinking about the first step. You try to supply the energy, the outer energy, into your control volume. Now those species, the fuel and the oxygen, they receive heat, and then they start to have a thermal decomposition and try to proceed the chemical reaction, but they have a negative effect coming from the flow. They will carry out the fuel, those very active species out of the main reaction region. Then this is the negative effect by the flow, right? Now you will think about, can we finish the ignition? Can we have a good ignition to start to let this flame be survive in the flow? They were determined by two time scale, right? The first one is the reaction time. You hope your supply heat is good enough, is large enough to initiate chemical reaction, and you believe the chemical reaction for the combustion is very fast. Then the reaction time is very short. Okay, if you have a short chemical reaction time, that means that ignition is easier to be achieved, right? But sometimes in your control volume near the ignition point, maybe you do not have enough fuel or enough oxygen. That means that if you are under a very thin mixture case, you understand, for a mixture, the very thin mixture case, the reactivity of the mixture is very low. That means they require a little bit longer reaction time to achieve, right? Short reaction time is good for ignition, but longer reaction time is bad for the continual burning flame. Now this is the meaning of the so-called catalyst reaction time. The other time scale is the so-called flow time. Since you already supply the heat from outer surrounding, for example, by the spark, electric and energy into your control volume, but those energy can be quickly to be removed by the flow. For example, you have a strong turbulent intensity, those turbulent eddies will carry the energy out of the control volume. Now you lost the energy, lost the thermal energy. Actually, they will tell you you do not have enough energy to initiate the chemical reaction for the burning flame, which means that if you have a short flow time, that means that your substance, your fuel and the oxygen cannot stay in this control volume for a longer, and this time is not long enough for reaction. Then they remove out. Then you are lacking of the fuel and oxygen for the reaction. Then you cannot have a good ignition, right? Based on the consideration on this time scale, you will find out, we bring these two to have a comparison. They tell you in this control volume, you already have a fuel and oxygen. Okay, now we supply heat to initiate their initial chemical reactions. Now there is the two time scales, they are competing. Okay, the flow time is too long. That means that they can stay in this control volume to initiate the chemical reaction and the complete reaction. Flow time large, if you have a large flow time, it's good for you to ignite the premixture. In the same sense, if the chemical reaction time is very fast, you still can have a good ignition. For both of them, you can see in the numerator flow time increase, or in the denominator reaction time decrease. one is increase, the other one is a decrease. Both of them will give you a chance to have a larger Danko number, which means if the Danko number is increased, then the possibility for ignition becomes stronger and stronger. You can perceive the chemical reactions. Okay, now you can now you understand the flow time, the competition between flow time and the reaction time. For the case of increasing Danko number based from is based described by the large flow time and also smaller or smaller reaction time. Conversely, if flow time is very short, flow time is very short means the fuel and oxygen may be carried away by the flow, or diffusion process very efficient. Then they cannot stay in the control volume to perceive the chemical reaction. Short flow time or longer reaction time will give you a decreased Danko number, right? In the denominator, flow time shorter, Danko number is shorter. Reaction time in the denominator is longer, then your Danko number is shorter. Both of them will give you the contribution to reduce the Danko number, which means a small Danko number will give you the idea that ignition may not be complete. Okay, then you cannot have a propagating premixed flame be ignited in your given flow. That means now you understand the meaning of Danko number. When you have a small Danko number, that means that ignition is not achievable. Okay, they are even you have a premixtures of fuel and oxygen, but they are still stay in a cold flow structures. But you try to reduce the chemical reaction time or increase the flow time, the Danko number will increase continuously. And you will see this figure tell you there is a two characteristic line for the change of burning rate by varying the Danko number. Okay, here the horizontal axis, this is a Danko number variation. From the left-hand side to the increase to the right-hand side, tell you the Danko number is continuously increase. Okay, and the corresponding burning rate can be viewed in the along the vertical axis. Okay, now there is the two curve. One is the so-called S curve here. Okay, S curve there is the two branch connected by the intermediate branch. The lower one we call this is a weakly reacting branch. The upper one we call this the intensive burning branch. Okay, and this is a typical S curve, and it can be described based on the activation number very large. Okay, the other one, when you increase the Danko number, you can see the burning rate is continuously increase with the Danko number without this abrupt change described by the S curve. And these two lines basically defined by the order of your activation number. Now we go back to see what is the meaning of activation number AC. Activation number is the ratio of activation energy divided by catalyst thermal energy. Okay, activation energy usually is very high, very large for a combustion process. And the thermal energy you can treat as so-called heat of combustion, because you release heat in your control volume and to be used to proceed the further chemical reactions. And you may consider this as supplied by the electric energy. However, you can see when these two energy compared together, as I mentioned in the combustion process, the activation energy is a higher order magnitude compared with the heat of combustion. Then this AC is a large value. Okay, activation energy is much larger than the heat of combustion. Now AC is very large, but if they are compatible, okay, activation energy, the amount of activation energy is very close to the catalytic thermal energy, then they will give you the idea they are in the order, first order, order one quantity. Order one quantity, that means that they are in the same order. In the same order, they tell you, in this situation, tell you the activation energy is not too high. Actually, the variation of burning rate influenced by the Danko number can be described by this monotonic increased curve. Okay, this is not belong to the burning characteristic of a premixed frame. But for the S curve, actually, they tell you activation energy is a higher order than the heat of combustion. Then the order behavior, the ignition and the extinction behavior will be described by this so-called S curve. Okay, now we try to pay our attention to the physical phenomena on this S curve. We start from the very earlier, we call this so-called the frozen state. Frozen state means in your control body, you have fuel and oxygen, they mix together, but maybe the temperature is low or the flow is very is closer to a stagnant. That means no movement. Now, in this state, maybe you cannot have any chemical reaction occurs. Then we call this as a frozen state, or you can describe it based on the so-called cold flow. Cold flow means in this state we do not have any chemical reaction occurs. Okay. Now you try to increase the Danko number. Okay, what is the meaning of increasing the Danko number? You can see one way you can increase the Danko number. That means that you try to reduce the chemical reaction time, right? Okay, you try to reduce the chemical reaction time or increasing the flow time. Okay, supposedly you start to provide a certain heat from the spark, and they will initiate the local chemical reactions. And a local chemical reaction, if you can continuous increase their decrease their reaction times, that means that you may try to change your concentration of fuel or concentration of oxygen, or you may try to put in some of the more active species to initiate. But those kinds of initiation may not give you a abrupt change, but they start to have a so-called weakly reacting mechanism, and you continue increase, and suddenly there's something happen. Something happen means here there is the turning point. Okay, I need to emphasize that actually the S curve basically is predicted by theory. In the experiment of real applications, we cannot see the intermediate branch between the extinction state and ignition state, because when you try to increase your Danko number up to a certain point, actually the burning rate is still continue increase. At certain point, then something happen. They start to have strong chemical reactions occurs, and at this point, now the burning rate will jump from the very small burning rate, very weak burning situation, to a certain high burning rate at these positions, the higher position. Then from the ignition state jump to the intensively burning branch. And at this point, the turning point of the lower branch represents the so-called the ignition state. Okay, ignition state means at this point the burning rate suddenly change from a lower value to a very high value, and you can see from experiment observation. Now you can see the flame exists here. Near the ignition state, you may see just have the light from the spark, electric spark, that is the supply coming from the outer outside. But when you have the successful ignition, the burning status will change from the weakly reaction state, jump to the intensive burning state. Okay, here from I jump to the upper branch. Okay, this is the status for the ignition defined by the so-called Danko number. Ignition starts from the frozen state, and we try to increase our heat supply from outside. Then the chemical reaction will be enhanced slowly, but at certain point, suddenly at the in the control body, the strong chemical reaction occurs. Then you will generate a propagating premixed frame. And in this case, the burning rate is very strong. Can we describe the state in the upper branch? Okay. And if you have this propagation premixed frame initiate, then this propagation premixed frame can survive and has a steady burning. They can continue propagating, or they can stabilize at certain points to with the balance by the subsiding of premixtures, and the burning intensity will keep almost do not change too much. And this is so-called the ignition achieved by the description on the lower branch of S curve. Okay, and conversely, you look at from the other way for very strong burning premixed flame. For example, here in the top right corner here, initially you may have a very strong burning. Very strong burning means in this control volume, the flow time is very short, and I'm sorry, the chemical reaction time is very short, but flow time is longer. Then the value of Danko number is very large. They will give you a chance to maintain a propagation premixed flame. The burning strength is strong, but you try to reduce it. Reduce the Danko number. How to reduce it? Simply, you can think about if you increase your flow, decrease your flow time. That means that you try to introduce more turbulent AD to carry out the thermal energy inside of your control volume. Now the control volume will lose thermal energy. Then this thermal energy usually used to support the preceding chemical reaction, but now this energy is reduced. Then the burning strength will be reduced gradually. Okay, you cannot quickly change that, but you can see that if you reduce the Danko number continuously, the burning strength is slightly decreased, but almost no change. But when you have a very large amount of energy carried out to the outer surroundings, the flow time or chemical reaction time change. Flow time reduced. Chemical reaction times increased. Both of them will give you a chance to reduce Danko number to a certain value. At this value, they have a suddenly change, reduction on the burning rate at this critical turning point. Then from the experimental observation, you feel you can see suddenly the flame disappear. Then there was a jump. If the flame disappear in the flow, that means the flow will return to a cold flow situation. No flame, no chemical reaction. Now this is a so-called extinction state. Now this from our experimental observation, this state will drop to the DAE. This is a Danko number extension, and the previous one for ignition we call this a DAI, Danko number for ignition. Okay, now when you bring these two ideas together, actually they bring the idea describing the transient state for the extinction and the ignition by this S curve. And they tell you initially you may have a frozen state, and you try to increase your Danko number to a certain value, Danko number at extinction. Then the other state will jump from I to the upper burning branch. The I state means that before the ignition state, there is no flame you can observe, but when you have an ignition occur, achieved, then they will jump to the flame. No flame and with flame will be between these will be identified by the ignition state. Okay. Conversely, originally a strong burning flame in the upper branch will suddenly disappear at the extinction state. That means at this point you have a flame, but suddenly extinction occurs, then the flame extinction disappear. Then you will jump to the lower weakly reacting branch. In the between the upper branch and the lower branch, there is the intermediate branch. Unfortunately, from the experiment, we cannot see any state can be described along this intermediate branch, because in the state described by the theory basically is unstable state. as a stable state means it is cannot be observed in our stable systems. Okay, but from the theory, we can connect these two by stability analysis. Then you will branch the upper branch, and you will bring the upper branch and the lower branch together by this intermediate branch. But anyway, they tell you, in reality, for this S curve, there is a two turning point. The turning point in the lower part described as an ignition state to be used to determine the ignition possibility, and the upper one is for extinction. Okay. Now this, I think this picture is clear to give you the idea to describe, to understand the transient state, especially for a premixed blend, for the extinction and the ignition. Okay. If you understand all the structures described by the S curve, based on the definition of Danko number and the activation number, now we will start to learn the ignition process.